what we need is storage or short-term memory storage for the predicate for the previous phone and word and the current phone and word. So these are as shown. These are modeling joint distributions over the word and the phone, and then a long-term memory fragment that binds together the previous and the current phone via the transition function. And this is the state transition function that we saw in the HMM. Similarly, for the perception, we require an observation predicate that is then combined with the state information through the observation function. So far we have just processed utterances in the graph. We haven't actually added any mechanism to select the most likely utterance. And that can be done easily via adding a separate predicate that holds the value of the most likely word and a conditional to be able to select that word. So what we are doing here is we are summarizing out the current from this joint distribution, and the selection happens via sigma's decision cycle. So how well does this do? The top row shows these graph structures declared using predicates and conditionals, but parameters were obtained from the hidden Markov model toolkit, and we were able to achieve state-of-the-art results with that. The bottom row shows the sigma's learning algorithm, actually gradient descent learning algorithm, learning these parameters, that is the transition function and the observation function, and we are able to obtain similar results with that as well. So I've been talking about being able to reuse mechanisms in the architecture. So can we reuse mechanisms, and how much can the architecture contribute towards the speech task? Well, it turns out that the architecture can do a lot for this isolated word recognition task. So there's a mechanism in Sigma which was added for reinforcement learning, action learning in reinforcement learning, and that's called action modeling, and it is able to actually create the top portion of the graph. Similarly, there was a mechanism added in Sigma to do map learning in SLAM, and that is able to actually generate the vertical portion of the graph. So what we really need to generate the left portion of the graph is really the predicate definitions, and that's it. The copy and so this copy here and this portion of the graph is generated by Sigma by itself. You still need the selection predicate and the selection conditional, and that is all that is really needed to do isolated word recognition. And we believe this is really cool, of course. So with these auto structures and using HTTP parameters and Sigma's learning, we were actually able to get state-of-the-art results. So here we were a bit more careful. We ran 5-fold cross-validation with randomized training order, so there is a slight difference in the stats, but these are again state-of-the-art in isolated word recognition. So to quickly wrap things up, what we have done so far is isolated word recognition. It's a simple real-world task, but we believe it's an important one to demonstrate Sigma's capabilities. It was implemented as knowledge on top of the architecture, and we demonstrated a lot of mechanism reuse. A lot of the portion of the graphs was generated automatically, and this we believe is an important first step towards our long-term goal of fusing language, speech, and cognition. The left, so this is a slide we just saw. The left portion is cognition, this is language, this was the work that I talked about today, and we are excited about the possibilities of the fusion of all these two.